Hello everyone. Today we will solve few more problems on analysis of shear strength of PSC members. Today's first problem. A concrete beam of rectangular section 200 mm wide and 600 mm deep is pre-stressed by a parabolic cable located at an eccentricity of 100 mm at midspan and 0 at the supports. If the beam has a span of 10 meter and carries a uniformly distributed live load of 4 kN per meter, find the effective force necessary in the cable for zero shear stress at the support section. For this condition, calculate the principal stresses. The density of concrete is 24 kN per meter cube. So here a concrete cross section is given. It is a rectangular section of 200 by 600 mm size, and cable is parabolic with maximum eccentricity of 100 mm at center of the span and 0 at support. And span of the beam is 10 meter, carries a load of 4 kN per meter. We need to find out what is the dead load. So find the effective force necessary in the cable for zero shear stress. The value of tau, what we are going to calculate, that should be 0. To make that as 0, what is the force we need to apply? What is the effective force we need to apply on the section, that we need to find out. Along with that, we need to find out what is the principal stress. So this is the details given. LS of the beam and cross section of the beam we have drawn. Live load, it is directly given 4 kN per meter. Dead load, cross section into density of concrete, 0.2 into 0.6 into 24, it is 2.88 kN per meter. So total load will be 6.88. So since it is parabolic cable, we need to find out the slope of the section cable. So by using parabolic equation, 4E star by L square into Lx minus x square. So at support means x will be 0, and first derivative of the parabolic equation will be slope of the parabola at end. So x equals 0, E star will be total depth 100. So tan theta or sin theta, it will be, the slope of the cable is 0.04. So for zero shear stress at supports, F should be 0. So if we made tau equals, if we want to make tau equals 0, so the F value what we are going to calculate should be 0. So that is the condition given. So to meet out that condition, the support reaction and pre-stressing force at support should be same. So WL by 2 minus P sin theta, that is the equation we have. So F equals 0, it will become WL by 2 is equal to P sin theta. So here P we need to keep it as unknown, we need to find out, and sin theta we have calculated, W is known, span is known. So on substituting we will get P equals 860 kilonewton. So if we apply the pre-stressing force of 860 kilonewton, then the shear stress will become 0. And at support section, bending moment due to pre-stressing force is 0, and bending moment due to dead load and live load is also 0. So in this equation, Fx equals P by A plus or minus PE by I into Y plus or minus M by I into Y. Here PE, since eccentricity is 0, PE term becomes 0, so that entire term will go 0, and moment due to dead load and live load will be 0 at support, so M by I will also be 0. So we remain with only P by A. So P value we have calculated 860 kilonewton, and area of section is known. On simplifying we will get Fx equals 7.2 Newton per mm square, and we made tau is equal to 0, that is shear stress as 0. So tau will be 0, and substituting in equation sigma 1 or sigma 2 Fx plus Fy by 2 plus or minus square root of Fx minus Fy by 2 whole square plus tau square. So here Fy is 0 since there is no vertical pre-stress, and tau we made as 0. So only we remain with Fx 7.2. So on simplifying we will get sigma 1 as 7.2 Newton per mm square and sigma 2 as 0. Next problem. A concrete beam having rectangular section 150 mm wide and 300 mm deep is pre-stressed by a parabolic cable having an eccentricity of 100 mm at the center of the span, reducing to 0 at the supports. The span of the beam is 8 meter. The beam supports a live load of 2 kN per meter. Determine the effective force in the cable to balance the dead load and live loads on the beam. Estimate the principal stresses at the support section. So this problem is also same as that of previous problem. The cross section is 150 by 300 mm rectangular section, parabolic cable with eccentricity of 100 mm at center and 0 at support. Span is 8 meter, live load is 2 kN per meter. We need to find out dead load. So we need to find out what is the P required. To balance dead load and live load means it is again same. To make shear stress as 0. So this is the data given, cross section and longitudinal section of the beam. So WL, it is 2 kN given. WD, we need to find out 0.15 into 0.3 into 24. We got 1.08 kN per meter. Total it is 3.08. So by using parabolic equation we can find out what is the slope of the cable. At support it is 0.05. So to balance dead load and live load, bending moment due to pre-stressing force at the center of the span should be equal to bending moment due to dead load and live load. So dead load, bending moment due to dead load and live load, it is WL square by it, since it is a UDL. For UDL with simply supported beams, bending moment at mid span will be WL square by 8. That should be equal to bending moment of pre-stressing force P into eccentricity, that will be bending moment due to pre-stressing force. So that should be equal. By using this condition, we need to find out what is the value of P. Pre-stressing force we need to apply. So P equals 246.4 kilonewton. So effective shear force at support WL by 2 minus P sin theta. So as we balanced bending moment due to dead load and live load and bending moment due to pre-stressing force, so obviously the shear force will become 0. So F has become 0. So if F is 0, tau equals FA y bar by, we have that formula. So tau will become 0. At the support, bending moment due to pre-stressing force and bending moment due to dead load and live load should be 0. So same, since eccentricity is 0, pre-stressing force will be, bending moment due to pre-stressing force will be 0, and due to UDL, bending moment at support will be 0. So again we remain with P by A for Fx. So we will obtain 5.475 Newton per mm square. So tau is 0. On substituting sigma 1 and sigma 2, we will get 5.475 Newton per mm square and sigma 2 as 0. Next problem, a cantilever portion of a pre-stressed concrete bridge with a rectangular cross section 600 mm wide and 1650 mm, that is 1650 mm deep, is 8 meter long and carries a reaction of 350 kilonewton from the suspended span at the free end, together with UDL uniformly distributed load of 60 kilonewton per meter inclusive of its own weight. The beam is pre-stressed by 7 cables, each carrying a force of 1000 kilonewton, of which 3 are located at 150 mm and 3 at 400 mm and 1 at 750 mm from the top edge. Calculate the magnitude of the principal stresses at a point 550 mm from the top of the cantilever at the support section. So in this problem, if you observe the figure, the depth of the beam is given 1650 mm, the span is 8 meter, As we know, in cantilever beam, top fibers will be under tension and bottom fibers will be under compression in regular beam. So to maintain that, we need to apply the pre-stressing force above the neutral axis, so that we can make the bottom fibers under tension and top fibers under compression for pre-stressing beam. So because of that, it is given at the top. The details of the cables or tendons is given at the top. So total we have 7 number of cables which are arranged like 3 at 150 mm from the top, then 3 at 400 mm from the top, and the remaining one is 750 mm at the from the top of the beam. It is carried with UDL of 60 kN per meter throughout the span inclusive of self weight. So no need to calculate dead load, and one point load is located at the end of the beam, which is 350 kN. So 1650 mm is the total depth, so centroid will be at the 825 mm from the top or bottom, since it is rectangular section. So P, it is pre-stressing. Initial pre-stress is given, stress is given, we need to find out. Each cable carries 1000 kN and we have 7 cables, so 7 into 1000 is 7000 kN. Area 600 into 1650, and my moment of inertia I equals BDQ by 12. So first we need to find out what is the actual centroid of the entire cables. By combining all 7 cables, we need to locate one centroid. So A1 means area of first 3 cables, A2 area of second 3 cables, and A3 the last cable. So Y1 distance of centroid of A1 cables to centroid of this section, Y2 distance of centroid of A2 cables to centroid of this section, and Y3 is single cable, which is third layer from centroid of the section. So we don't know area, let us keep it as a constant A. So since we have 3 cables at top, we will be having A 3A, again second layer 3A, first layer 3A. So here we are calculating centroidal distance from the top edge. So from top edge we have 342.85 mm as the centroidal distance for tendons. So therefore eccentricity 825 minus y bar, so it is 482.15 mm is the eccentricity. So shear force at the support F equals support reaction 350 plus 60.8. Since we have only one support, the same load will be its support reaction. So 830 kN will be the support reaction. Bending moment at the support, again same 350 into 8 load into distance plus 60 into 60 is the UDL, 8 is the length, and 8/2 is the point of application of UDL. So moment we will get 4720 into 10 power 6 Newton mm. So in question he is given, we need to find out the principal stress at the location where we have 550 mm from the top of the section. So A y bar, so area, if we want to calculate area, 600 will be width and 550 mm will be depth, into 825 minus 550 by 2. So AY bar we will get, and B is 600. On substituting this, we will get 1.12 as the shear stress. So Fx P by A plus PE by I into Y minus M by I into Y. So on substituting all the values, we will get Fx value 5.42 Newton per mm square. So again principal stress sigma 1 and sigma 2, Fx plus Fy by 2 and substituting all the data, we will get sigma 1 as 5.64 Newton per mm square and sigma 2 as 0.222 Newton per mm square. Next problem, a pre-stressed concrete beam of span 10 meter, a rectangular section 120 mm wide and 300 mm deep is axially pre-stressed by a cable carrying an effective force of 180 kN. The beam supports a total UDL of 5 kN per meter, which includes the self-weight of the member. Compare the magnitude of the principal tension developed in the beam with and without axial pre-stress. If a curved cable having an eccentricity of 100 mm at the center of the span and 0 at support is used and effective force in the cable being 180 kN, estimate the percentage reduction in principal tension in comparison with the case of axial pre-stress. And third case, if the beam is additionally pre-stressed by vertical pre-stress of 2.5 kN per mm square in the curved cable, estimate the principal stresses developed at the support section. So in this problem we have three different conditions for solving. So first we need to calculate the principal stress. What is the principal stress if we are not applying the pre-stressing force? And for the same condition, if we apply the axial pre-stress, what will be the principal tension that we need to find out and we need to compare. In second case, okay, if we replace that straight tendon, axial tendon, with curved tendon of 100 mm eccentricity at center and 0 eccentricity at support with a pre-stressing force of 180 kN, how much principal tensile stresses will reduce in comparison with first case? That we need to find out. And third case, along with that, if we add vertical pre-stressing force of 2.5 kN per mm square, what are the stresses developed in the section? That we need to find out. So first, W, it is a live load given 5 kN per meter, area to 120 by 300, IBDQ by 12 since rectangle section. P 180 when in case of P is the effective pre-stressing force. So shear force, since it is simply supported beam with UDL, load by 2 will be the support reactions and that same will remain as the shear force. WL by 2 is 25 kN. F equals 25. So B is 120, AY bar we have. So if we calculate tau, so shear stress, it is 1.04 Newton per mm square. So first let us start with first case. Principal tensile stress at support section without axial pre-stress. So we don't have any pre-stress here, so Fx and Fy both will be 0. So in that case we remain with only shear stress, it is 1.04 Newton per mm square. So if we apply the axial pre-stress, that is horizontal pre-stress, Fx, so bending moment due to pre-stressing force at support will be 0 as we have eccentricity of 0, axial pre-stressing, so PE will be 0, Fx will remain with only P by A, so Fx will be 5 Newton per mm square. Then again substitute in the same principal tensile stress equation and solving, we will get sigma 2 as 0.207 Newton per mm square. So you can compare here, without pre-stressing force we have 1.04 Newton per mm square and with pre-stressing force we have 2.207 Newton per mm square. So if you consider the percentage, it is almost 80% of shear stress is reduced in the beam. 80.09% of shear stress is reduced in the beam with axial pre-stressing. Now again we will replace the axial pre-stressing by parabolic profile with eccentricity of 100 at center and 0 at support. So since parabola we need to find out slope 4e star by L square into L minus 2x. It is first derivative of parabolic equation we have directly considered here. So x will be 0 at support, sin theta is 0.04. So effective shear force, since we have a pre-stressing force with both horizontal and vertical component, WL by 2 minus P sin theta. So F equals 17.8 kilonewton. So here effective shear force will be 17.8 kilonewton. Tau V shear stress is 0.74 Newton per mm square. So Fx we have calculated earlier with pre-stressing force. We will be having 5 Newton per mm square at support. So on substituting all the values, we will get 0.107 Newton per mm square. So again you can observe with straight it is 0.207, with parabola it is 0.10 minus 0.107. So minus means the tensile stress is totally eliminated and you arrived with compressive stresses. So 100% of tensile stresses are eliminated here. So again see, you can observe in comparison with axial pre-stressing, 48.3% of stresses are reduced with respect to straight tendon and parabolic tendon. If we again add 2.5 Newton per mm square of vertical pre-stress, so here Fx we have calculated 5 Newton per mm square and Fy we are adding here 2.5 Newton per mm square additional. Tau is same. So in that case 2.29 Newton per mm square compressive stresses are going to develop in the member. So here there is no tensile stresses. Here it is compressive stress only. 2.29 Newton per mm square. Thank you. Next class we will start with design of shear transfers or shear reinforcement for PSC members. Thank you.